Hi, today we're looking at Module 4, Lesson 8, replacing numbers with letters. Yesterday we looked at taking the letters and replacing them with numbers. Today we're going to take the numbers and replace them with letters. And while we're looking at that, we're going to review the properties, which hopefully will sound like a review from elementary school. But just in case, we're going to go over all of it. So we have 5 statements here. Are all of these statements true? Yes, all of these statements are true. How many of these statements would be true if the number 4 was replaced with a 7? 7 plus 0 is 7. 7 times 1 is 7. 7 divided by 1 is 7. 7 times 0 is 0. 1 divided by 4 is 1 over 7. Are they all still true? Yes. Would the number sentences be true if we were to replace the number 4 with any other number? Any number. Just the 4. If we left the 1s and the 0s the same. Would it work? Most of them would work. The only one that would not work would be for the division. Okay? If we replace the number 4 with the number 0, then we would have a problem. So let's take a look. If we replace all the 4's with 0, they would all be true except the last one. So no. The first 4 are true. No matter what number we use, the first 4 are true. But the last one, dividing by 0, is not true. Okay? So no matter what number we change 4 to, all of those statements are true. Unless we use 0, and the last one's not true. Okay? So hopefully you have this answer written down in your notes. So basically, we're saying that 4 can be any number. What can we use to represent any number? What can we use? We can use a variable or a letter. So we're going to use the letter G for today. So let's rewrite all 5 expressions below, replacing them with a G. Okay? So we have G plus 0, and I get G again. G times 1 gives me G again. G divided by 1 gives me G again. But G times 0 gives me 0. And 1 divided by G equals 1 divided by G. Because remember, the fraction bar means division, right? So are all of these true except for when G equals 0 when dividing? Yes, as long as G does not equal 0. Now, each one of these examples is a property. So we're going to look at each one of these number sentences a little more closely and see if we could come up with some statements or truths or claims or theorems. Sound like fun? Well, we're doing it anyway. Okay, ready? The first example is the first sentence, G plus 0. Let's look at this one a little more closely. You ready? Ready? Come on. Okay, replace a letter in the mathematical expression represents a number. Remember that a letter in a mathematical expression represents a number. Can we replace G with any number? Yes, we've discovered that at great lengths already. So let's choose any letter for G. If G equals 7, 7 plus 0 equals 7. If G equals 49, 49 plus 0 equals 7. Hey, how about 13.1? I like that one. Get math on. So 13.1 plus 0 is 13.1. Yes.
You said 49 plus 0.
Sorry. So is this number sentence true regardless of the value of g? So no matter what g equals, is that value true? No matter what g is, are all these sentences true? Yeah, they're all true. They all make sense. They're all the right answer.
Well, what you said, no matter what g is.
Well, this is for addition. So even if g is 0, let's see if g equals 0. 0 plus 0 equals 0. So for this sentence, no matter what g is, it will be correct. Because why? What kind of a statement can we say about all of these number sentences? What happens? What's the same with all of them? G kept changing from one equation to the next. But what was the same? What's kind of the rule? What do we see happening here in all of those number sentences? How do I end up with the number that I started with? Right, what did I do to each one to get my identity back and get the same number back? What did we do every single time? Give me a better word than nothing. We added 0. Okay, we added 0. Okay? So we were able to notice the value of g did not change when 0 is added to g. Okay? So that actually has a name. Does anybody know the name of that claim, that rule that you just made? What is that called? Yep, it's actually the title of that lesson. So g plus 0 equals g is called the additive. Additive identity property of what number? Help us out. Get our identity. Keep our identity. 0. So whenever I add 0, I keep my identity. So any number added to 0 equals itself. Okay, so to summarize, the additive identity property of 0 means that 0 preserves the identity of every number during addition. Okay, so addition and 0 keep the identity. So no matter what number we're using, which here is represented by A instead of G. Let's take a look at the second number sentence that we had talked about. We have G times 1 equals G. So right away we see G, we're getting G back again as our answer. So again, we have our identity. This time, how are we keeping our identity? It's not adding 0. What can you say about looking at that example? Because we already said they're true. We tried them out with a lot of different numbers. Right, so multiplying by 1 works the same as adding 0. It keeps the same identity. So let's take a look at the questions. Remember that a letter in a mathematical expression represents a number. Can we replace G with any number? Can we? Yes. So if G equals 3, 3 times 1 equals 3. If G equals 49, 49 times 1 equals 49. If G equals 13.1, 13.1 times 1 equals 13.1. So no matter what number, we tried a couple examples. So with each of our examples, no matter what we change G to, is the statement still true? Yes, this statement is still true. All of those number sentences are correct. So what that means, G times 1 equals G. So now we multiply. So this is the multiplicative identity property of what number? What number when we multiply helps us keep our identity? 1. Exactly. So we can summarize by saying any number multiplied by 1 equals itself. Okay? Pretty straightforward. So adding 0 keeps the identity, multiplying by 1 keeps the identity. So far, so good? Any questions so far? Does this sound a little familiar? You've discussed these properties before. But not only are we looking at the properties, we're realizing we could replace a letter with a number, as long as that number is the same every time you see that letter. So to summarize, the multiplicative identity property of 1 means multiplying by 1 preserves the identity of that number. So no matter what number is A, we get A back when we multiply by 1. Okay? Okay. How about I'm grabbing a test today? All right, let's look at example 3. Now, replace the 3 in these equations with the letter A. So right now, what's the matter? Let's rewrite these with the letter A. Pick up your pencils and let's rewrite them. A plus 4 equals 4 plus A. A times 4 equals 4 times A. A plus A plus A plus A equals 4 times A. 3 divided by A equals, sorry. It's a little confusing. A divided by 4 equals A divided by 4. So now let's see if we use any other letter for A. Will those statements work? God bless you. Yes, they will. Okay? We can replace A with any number, and we know that they will all work. Now they want us to rewrite them again, but this time change the 4 to a B. So let's do that now. So A plus B is the same thing as B plus A. A times B is the same thing as B times A. A plus A plus A plus A equals B times A. A divided by 4, oops, I didn't go to that last one, always get me. A divided by B equals A divided by B. So we took all of our numbers and we replaced them with letters. And the statement is still going to be true. Instead of using 3 and 4, I could replace A with 7 and B with 9, and those statements would still be true. Sorry, say that again?
Since it has A, B times, wouldn't B still have to be 4?
Every time we change the A, that's what I was thinking. We'll take a look at that.
To add more A's.
Right, that should still be a 4. No, it can be a B. I'm going to go back and take a look at that, because that's what I was thinking too. Are the first two sentences always true? Well, here's the thing. Let's read the next question. Are the first two sentences always true for all values of A and B? Yes, the first two are always going to work. Will this one always work? No, that one's not always going to work. It's just not gonna work, okay? The last one will, because it's A divided by B, it's A divided by B. So, but look, does it matter if we add A and B and we, B plus A, does order matter? Nope, order doesn't matter. What about for multiplication? Does order matter? Nope, order doesn't matter. What about for division? Does division matter? Yes. These are not necessarily going to give me the same answers either. Okay? A divided by B is, this is actually B divided by A. B divided by A is not the same thing as A divided by B. So if we look at these two examples, we see that order doesn't matter, okay? If we plugged in numbers, we would be able to prove those, but for time's sake, you all know and you can do examples in your head, okay? So this is called A plus B equals B plus A. That's called the commutative property. Of addition. And then A times B is the same thing as B times A. And that's the commutative property of multiplication. So to summarize, order does not matter when multiplying or adding. Because if we replaced A with 4 and B with 2, 4 plus 2 is the same thing as 2 plus 4. They both equal 6. 4 times 2 is 8. 2 times 4 is 8. So those were equal. But here, 4 plus 4 plus 4 plus 4 equals 16. 2 times 4, that does not equal 16. So that statement didn't work. 4 divided by 2 is not the same thing as 2, I keep saying it backwards, 2 divided by 4. Now I'm saying it backwards again. 4 divided by 2 is not the same thing, but it is the same thing as 4 divided by 2. But how we would set it up, that would be 2 divided. We're going to come back to this one because I just confused myself, so I apologize for that. Okay, but you know that division is not commutative. Order does matter. I just picked two bad examples. All right, so that was a big bobble on the video. You ready? Let's continue. So here's examples of the commutative property of addition. 4 plus 3 gives us the same total as 3 plus 4. A plus B gives us the same total as B plus A. So order doesn't matter when we're adding or multiplying. The same with multiplication. 3 groups of 4 is the same thing as 4 groups of 3. So those are both 12. So you can call those the flip-flop. Commutative property is the flip-flop. Order doesn't matter. I like to think of it as the word commute. Here I am in my house. Okay? And here is my work. Here's good old Great Hollow. When I drive to work in the morning, it's 10 miles. And what about when I go home? It's still 10 miles. It's the same value no matter which way I'm going when I'm commuting to work back and forth. Okay? Now, I'm going to stop the video because we have a sprint to do. So let's see how we do. Take out a sheet of loosey paper quickly.